Well, that's not ideal. But that's the way it goes, right? Right. Conservative again. And then there's contact. Then there's resistive. Anybody watching at home, the program crapped out. So if you're one of these 6 people absent today in 6th period, you're trying to watch this, you just have to restart. So conservative force, gravity, which we call weight. There's an expression we use for the weight. It's a product of the mass of the object times the acceleration of gravity. Most forces, we don't have an expression for them. They're solved in context. But there are a few that we have an expression, and that's one of them. So going back to our little dot acting on our object, our dot acting as our object. We look at the book acting on the table. Do we think that the book is experiencing weight? Is it near the surface of the earth? The answer is yes, then you draw a downward arrow to indicate the weight of the object. More importantly, keep this in mind, this is setting the scale for all of the other ones. Whatever length arrow you draw here, the other forces you're going to draw are going to be relative to the size arrow you use here. So have a little foresight. It's not done until it's labeled. And you can label it either a W or mg. I will often label it mg because there's usually multiple masses in our system, and so they'll have m1g, m2g, something like that. So that's easier than weight 1, weight 2, in my opinion, but it doesn't matter. Weight or mg is a fine label. Next, there are contact forces. This is not an exhaustive list, by the way. It's just a starting out list. We have normal forces, and we have tension forces. I'm going to use N for normal and T for tension. Normal forces are pushing forces and occur at surfaces. But here's the important thing. These are rules, by the way. Just like gravity is always down, contact forces have rules. The normal force is called the normal force, not because it's ordinary, but because of the geometry word normal, which means perpendicular. All normal forces are perpendicular to the surface in contact. I'm not writing that down because it's too many words, but it goes right here. I'll write this little symbol. That's the perpendicular symbol. All normal forces are perpendicular to the surface in contact. An object can be in contact with more than one surface. Don't assume that there's always just one surface involved. I can walk over there and push down on the top of the book, or lay something on top of the book. That would be a surface on the bottom, the table, and whatever's on top, laying on the book, another surface causing a force on the book. So you can have multiple surfaces causing forces on a single object. In the same way that I can have multiple ropes or cables or strings attached to a single object, there can be multiple tensions. But tensions are pulling forces, and they are always in the direction of the string or the cable or the rope. So pay attention to the direction of the string. And I'll use the word string here, but there could be any number of things. Thread, cable, handle. Now evaluating the contact force. Is there a surface in contact with the book? Yeah, the table. Can we all agree that the table is level? That suggests that I will draw a normal force that is perpendicular to the table. And as I think it's the only thing pushing up on the book, I'm trying to be careful to draw this force to demonstrate a certain amount of balance and scale. I think it's the normal force that's balancing the weight. So I'm drawing it carefully to try and draw to scale with the normal force a similar size to the weight. Are there any strings, cables, ropes connected to the book? Don't see any, so no tensions. We are done with our contact forces. Moving on to resistive forces. For resistive forces, we have friction and air resistance, also known as drag. I will use a capital D for drag, but friction we usually use a lowercase f. That's out of tradition. There's no air resistance in a problem unless you're told there's air resistance in a problem. So don't go looking for air resistance unless it's given to you. Everybody got it? They'll say whether there's air resistance or a resistance from a fluid. On the other hand, friction you might have to interpret. Friction is a force to prevent one surface from slipping past another. Again, friction is a resistive force that attempts to prevent one surface from slipping past another. Try to prevent a surface from sliding. There's two kinds of frictional force. There's frictional forces that hold an object from moving, and then there's frictional forces for when an object is already sliding. There's two kinds. So when you're applying the idea of friction, understand that if there's motion, well, then that's a sliding friction, and it's going to oppose the motion. If it's not moving, then it's got to be directed in such a way as to try and prevent the object from moving. But be careful. It doesn't have to be any friction. You have to evaluate your situation. But if you're listening closely to what I said, it should be clear that friction is going to be parallel to the surface. It has to be. It's trying to prevent one surface from sliding past another. So it must be parallel to the surface. And if you're really paying attention, you realize that friction has to be perpendicular to the normal force. If the normal force is perpendicular to the surface, and the frictional force is parallel to the surface, then normal and friction are perpendicular to each other. That's right. More pencils should be wiggling. You're going to screw it up later, and I will have told you how not to screw it up. I'm going to add to this something that should be blatantly obvious. But if there's no normal force, there's no friction. Right? To have friction, one surface has to be touching another. So if the surfaces aren't touching, there's no friction. But the moment they're touching, there's a normal force. So normal force and frictional force are related. Do we believe there's any friction acting on the book right now? I think the table is horizontal. And I'm looking at my picture. And my picture kind of indicates that the forces are balanced. Friction would have to be acting in such a way as to prevent the object from sliding. But I don't think the object's sliding. You follow what I'm saying? Where would I draw friction? To the left? That would mean that it'd be accelerating to the left because it'd be unbalanced. I think we can stop right here and say that there's no frictional force acting on the system. Now, we have evaluated all of the forces. So now, we go to the next part. We want to apply a coordinate system and deal with off-axis vectors. That's the next part of this. Now, applying a coordinate system has two priorities. Which means you apply priority 1 first. If priority 1 isn't necessary, then you apply priority 2. Priority 1 states to choose a coordinate system with a positive direction placed in the direction of the acceleration. So we choose a coordinate system with a positive direction placed in the direction of the acceleration. That is the first priority. If your system is accelerating, it has to be the positive x or the positive y direction. I would strongly encourage you to do it this way, because if you don't, it becomes very difficult to solve the problem, because it means your acceleration is not along a coordinal direction. If your system's not accelerating, you don't have to obey that priority. So the second priority is to line up your system with as many forces as possible. Now, I have to say this because there's going to be like one or two of you in every class that thinks that you can draw X and Y any which way. That's not true. If I decide to make the, If I decide to make the X direction that way, then the Y direction has to be perpendicular to the X direction. I can't just decide to make the Y direction this way for funsies. So when you're drawing a coordinate system, X and Y are perpendicular to each other. So although I'm saying line it up with as many coordinates as possible, what I'm saying is find forces that are already at right angles to each other and line it up that way. This one is stupid easy, right? I'm going to make the Y direction that way and the X direction this way. Told you the first one is super simple. Now, the free body diagram actually ended once we had the arrows in place. What we are doing now is adding stuff to our diagram. You may be instructed to not do this on a test and do your work somewhere else. This is doing your work somewhere else. Now, choose a coordinate system. Deal with off-axis vectors. If you have any vector that's drawn off-axis, you have to deal with it now. You have to do the trig and break it up into components. This one has no off-axis vectors, so we don't have to worry about that. Everybody good? All right. We are done with this portion, so we can put that away. There we go. All right. Our last one, apply Newton's laws. We chose which law to apply at the very beginning, so we're applying it now. Once we said that it was net force equals 0, then it is net force equals 0 in both the X direction and the Y direction. Applying Newton's laws. It's one-dimensional for us, meaning we're only dealing with one-dimensional problems. But this isn't an equation. It's not even an expression. It's directions. You need to follow these directions. The first direction is to add up. All of the forces in a particular direction. Taking the direction into account, meaning making them positive or negative, and set them equal to 0. It's directions. It is telling you what to do, but it is a set of directions. Add up all the forces in a particular direction, taking the direction into account, and setting it equal to 0. Now, there's nothing to do in the x direction. There are no forces pointed that way, but I have a force pointed up, positive n. I have a force pointed down, negative weight, set that equal to 0. That is the result of all of this work, is to come up with a relationship that may or may not be able to solve your problem. It should be able to. We're analyzing it. There's not a lot to analyze here. I was really just using the book on the table as an example. All this would tell us is that the normal force equals the weight. That's all this would ever tell us. That may or may not be important. But again, this doesn't solve your problem. It gives you a method to solve your problem. All right. Ready to try this for real on something more complicated? Okay. So, all right. If we look at the set of rules that we've talked about already, let's see, where is it? Right here. Let's see, we wanted to do, we have priorities here. So let's deal with our priorities next. So I'm going to divide this up again because I want to make sure we do this. So I'm going to divide it in half-ish. I'm going to come up with our new problem. This is example number 2. Can I borrow somebody's? So in this example, the calculator is sitting on the cover of the book. So there's the cover of the book. And I think it was pretty clear that I tipped it up at a pretty steep angle. So does that picture represent what I did with the calculator? We are interested in the calculator, not the book. So start by drawing a free body diagram. I'll help you out. Step 1, a dot to represent the calculator. You do the rest. We said that this is a Newton's first law problem, so I'm going to write that up there too. You have a set of rules, and they're not particularly hard rules. I'm going to go through a set of questions for you guys that corresponds to the set of rules you've already discussed. So, I'm going to start by saying, is there a conservative force acting on the object? Yeah, there always will be. So be the smart person and jump on that one and say, yeah, there is. There's got to be a force downwards. I'm going to call that weight. All right, moving on from conservative forces to contact forces. Was the calculator in contact with the surface? Yes. Yes, it was. It was in contact with the surface of the book. That's a normal force. And normal forces must be drawn perpendicular to the surface. That would be this direction because that's the direction of the surface. So when I draw this force, I'm going to draw it at an angle that represents perpendicular to the surface. I don't necessarily know how long to make this vector. I may have to adjust it in the future, but it has to be in this direction. And I will label it a normal force. This does not appear balanced to me. So maybe there's something else acting on the calculator to hold it in place. Otherwise, it would travel probably that direction. And I think you can imagine a situation where it slides down the book. Well, are there any ropes or strings that were connected to the calculator? So there must not be a tension force acting on the calculator. Is it possible there was a resistive force that was acting on the calculator to prevent it from sliding down the ramp? Seems not unreasonable. That force would have to be parallel to the surface. So I'd have to draw it in such a way that it was perpendicular to the normal force and parallel to the surface. So all of you smart people who I walked around and I saw forces pointed straight upwards, no. It would have to look just like this, with these two forces perpendicular to each other. That's it. We're at the end of the list. So all of you correcting yours right now, you understand why I said you need to be good at this, you need to be fast at this. There's nothing particularly complicated about any of this. That doesn't make it easy. So next, we have to draw a coordinate system. When I draw this coordinate system, I choose these priorities. Priority number 1, is my system or my object accelerating? It's not. So I can choose priority 2, which means I can choose the direction I want to set my X and Y. I could choose to do it this way. But based on priority 2, this might be a harder way to do the problem. If I do it this way, yes, the weight is perfectly in line with the y-axis, but now the friction and the normal force are not. I know that the normal force and frictional force are perpendicular to each other, so it might behoove me to choose a coordinate system that helps me deal with the fact that they're at right angles to each other. Now, I only have one force that would have to be dealt with. One force where I'd have to do trig. So the weight is an off-axis force. I would have to resolve it into components that lie along the y direction and along the x direction. There's probably a relationship between this angle and one of these two angles. We'll have to figure that out. There's some geometry there. And you guys who are so smart, got A's in geometry, you should be able to figure that out. There's probably some similar triangles or some complementary triangles there. You guys are so smart, or at least like to think so. But if we get past that, then I think we can say that this is a decent coordinate system. We all good with that? So our next job is to apply Newton's law. Well, I have net force in the x direction equals 0, and net force in the y direction equals 0. I must add up all the forces, taking into account the direction, and set them equal to 0. So in the x direction, I see two possible forces. I see friction in the positive direction and a component of the weight in the negative direction. I'll have to figure out that component. I'll probably have to do some sine, cosine, and tangent, right? I think the weight looks like it's an opposite side, probably going to have something to do with the sine of an angle. In the y direction, I've got normal force, positive y direction, and weight. The weight in the y direction seems to be an adjacent side, probably going to have something to do with the cosine of the angle. Probably be working on that, huh? I'm seeing some sine and cosines in our future. We good? Done. It created two relationships that might be able to be used to figure out whatever our problem is. We'll see. Example number 3. Sometimes you are just told there is a force acting on your system. It may not fit conveniently into the mold of the other forces that are there. You're just said, here's a force, use it. We call that an applied force, and generally it's a contact force. So here's your example of a system that might have a force that is given to you. I want you to imagine I am pressing the book against the wall and I'm applying a force to the book at a bit of an angle with my hand, and the book is sliding up the wall at a constant velocity. You all see that? I would like a free body diagram that would detail that experience, what we all just witnessed. I will happily draw a picture of this so you would have something to base your notes on. What I saw was that there was a book that was placed against the wall, and some guy pushed on the book, and subsequently the book went upwards at a constant velocity. This force that was just given to us is an applied force. You'll have these in problems. A kid pushes on a box, a guy pushes on a lawnmower, something like that. I would just list them as FA. They're a contact force, but generally they're given to you at a specific direction, and they are just a portion of your problem. I would evaluate them when you evaluate the contact forces. But be careful. Your free body diagram rules still are in force, which means if you're going to put this force in your free body diagram, it starts at the center of mass of the object and points away, even if it's drawn like this. Everybody understand? This is demonstrative. So start drawing your free body diagram, please. I'll give you just a minute or two. Guys, is there a conservative force acting on the box? Or acting on the book? Did you draw a downwards arrow? That's a good way to go. So I'm going to draw a downwards arrow as well. Is the book in contact with a surface? Sure, it's in contact with the wall. The wall must apply a normal force to the book. That normal force has to be perpendicular to the wall. We know some guy was pushing on the book. There's an applied force on the book that was given to us that we must use and evaluate. Now, the book was clearly sliding up the wall. Is it likely that there was a resistive force acting on the book? Yes, there was. Was that force acting upwards or downwards? Really? The force is attempting to prevent the book from sliding up the wall. Do you think the force was pulling the book up the wall? I don't. I think this acts downwards, not upwards. There's two ways you could do a force or do forces when you have them in the same direction. I tend to be a side-by-side kind of person, but you can also stack them, and that's just as good. So I like the side-by-side. Some people like them stacked. It makes no difference to me. It's supposed to show balance. So stacking them kind of tells you it must have that much downwards, there must be that much upwards. But I tend to be a side-by-side person. It's just the way I do it. You can choose what you want. This is a net force equals 0 problem. I said the object was traveling at constant velocity. It's sitting right there. That's the free body diagram. I'm not sure it's particularly well drawn to scale. I might need to adjust some of these forces to bring it more into scale, but we don't really have enough information necessarily to know how big they all are, but it should be kind of appropriately drawn. Now, from here, coordinate system, I'm probably thinking that the best coordinate system for this one right? It's not accelerating. This is lined up with 3 of the 4 forces. This seems like the most appropriate coordinate system to use. And based on where the angles all are, that's theta. Because I know about vertical angles, and I hope you do too. Example number 4. I am the owner of a business. My business is in a strip mall. That business has a doorway and an awning over the top of it. I would like to hang a sign so people who are walking next to where the doorways are, there's my doorknob, can see the name of my business. It is hung there by 2 ropes. A rope like that and a rope like that. Can you draw a free body diagram that would describe the sign?